So Syed, our next presentation, we'll be talking about application of thermoelectric technology in sustainable pavement structures. And Syed, if you want to share your screen.
Well, can you hear me?
Yes, we can.
All right. Hello, everyone. I hope you all are doing well. I am Syed Amitami, PhD candidate at Department of Civil Engineering at University of Texas at San Antonio. And today I'm really glad to have a chance to talk about my work. And my work is about application of thermoelectric technology in sustainable pavement structures. And I have to add that my topic is kind of similar to Muhammad Reza's. Actually, it's about energy harvesting, but here in this research, we try to use another type of energy within our asphalt structures. So my presentation will include introduction, goal and objectives, design concept and fabrication, finite element modeling, laboratory testing and results, and at the end, we will have conclusions. Well, as an introduction, we can see the population is increasing and our cities are expanding. So it could increase the demand of high performance transportation infrastructures. So the current roadways and the ones which are supposed to be constructed should be upgraded to smart roadways. And to accomplish this, we need to use and employ high advanced technologies in our roadways, such as structural health monitoring devices or communication systems, wireless sensors, and not only that, the intersections in remote areas are experiencing high rate of crashes due to lack of night visibility. So we have to employ such systems in our roadways, but there is a common problem among those systems to be activated and implemented in our roadways. And that issue is supplying power, because we cannot rely on power grids to provide power along our roadways, because it would be so expensive, and in most of the regions it could be impossible. So here we try to use energy harvesting. Energy harvesting could allow us to take advantage of the unused energies in our roadways. For example, here in United States, we have 6 million kilometers of roadways which are paved with asphalt pavement. And as you know, asphalt pavement could absorb a lot of heat energy, and this could increase the temperature of pavement up to 60 or even 70 Celsius degree. So this source of energy is always available and it is unused, so we can take advantage of that to produce electricity. So in our research, we try to develop and optimize thermoelectric energy harvesting for our roadways. And to accomplish this, at first we try to identify the optimum design for our prototype to produce high power out of that. At first we use Abacus for simulations to identify the best design for our prototype. And after that, we try to evaluate the factors affecting the performance of our prototype. At first, we evaluated the temperature of our pavement. We tried 45, 55, and 65 Celsius degree, and then we evaluated the size of TEG, number of TEG, and the TEG configurations. I will explain about TEG module in next slide. And after that, we have tested our prototype in the lab and in the field to evaluate the performance of our prototype. Well, here you can see the most important part of our prototype, which is thermoelectric generator, or TEG. TEG is a device with a 4 centimeter by 4 centimeter dimension, and it has two sides, hot side and cold side. So if we provide temperature difference across these sides, it could be activated and produce electricity. So our job here is that to supply and create temperature difference as much as possible to maximize the power output of our prototype and this device. So to accomplish this, this is the prototype that we came up with that. In left figure, you can see the schematic of our prototype. Our prototype is gonna be placed at the edge of road pavement. You can see part of that is inserted in a pavement, and the other part of that is gonna be placed in the surrounding soil. And this prototype includes 4 main components: L-shaped copper plate, TEG, which is attached to the bottom of plate, heat sink, which is filled with phase change material, or PCM, and we have an insulation box. So our copper plate is inserted 3 centimeters below the surface of asphalt concrete in order to absorb the heat and transfer it down where the hot side of TEG is attached to the copper plate. And our heat sink is going to provide cold temperature to the cold side of our TEG. So by this technique, actually we created temperature difference, so our device, our TEG module would produce electricity. And also here you can see the design of our insulation box. Actually, this is our insulation box, and the function of that is to minimize the heat exchange between the soil and our heat sink. So we designed this insulation box, which is composed of aerogel cover, foam box, and PVC. And here you can see our copper plate, L-shaped copper plate, and the vertical part of that is insulated with aerogel, which has a very low thermal conductivity. And this material was initially introduced by NASA for the first time for its spacecraft. At the bottom of that, you can see we have attached our TEGs at the bottom of this copper plate to absorb the heat. And here you can see our heat sink, and that's gonna be filled with phase change material. And then you can see the layer of our insulation box, aerogel and styrofoam, and the outer layer would be PVC for our insulation box. And here you can see our phase change material, or PCM. PCM is the material that could absorb the heat without changing its initial or performance temperature. So here we use the microcapsulated PCM, and it's like a powder. So we use it to maintain the temperature around 18 for cooling purpose. And here you can see this is our heat sink, which is filled with PCM. And we also inserted the thermal sensor to record the temperature variation over the time. Well, here you can see our Abacus simulations. We have conducted 2 sets of simulations for determining the optimum design. At first, we perform transient state analysis. And for our input for simulations, actually we measure the temperature at 4 depths of pavement and soil for 5 days, and we use them for our input. Also, we run our analysis from 11 a.m. to 7 p.m. for a period of 8 hours, because in these 8 hours, the pavement would experience the highest temperature during the day. So that's why we selected this period for our simulations. And at first, we tried to compare the performance of Z-shaped design and L-shaped design with the widths of 15 centimeters. So in table, you can see the top plate, both of them would experience the temperature of 46 Celsius degree. But at the bottom of the plate here, we are talking about this location. Here where the TGs are attached, we can see the L shape could deliver the temperature of 37 Celsius degree. So it shows that it's performing better than Z shape. And eventually you can see the delta T that the model with L shape could experience is about 13 Celsius degree. So here we selected L-shaped design for our prototype. And next, we evaluated 3 widths, 15 centimeter, 20 centimeter, and 25 centimeter. And again, here we found out that the prototype with 20 centimeter width could deliver the highest delta T for our TEGs here. So for our design, we selected L-shaped design with 20 centimeter width for our prototype. After that, we conducted a state analysis for these simulations. Actually, we tried to see the effect of number of TEGs. We wanted to see if we increase the number of TEGs, what will happen to the power, to the amount of heat that each TEG would absorb. So we proposed 5 models, A, B, C, D, and E. And the difference between the model D and E is that both of them have 4 TGs, but in the case of E, you can see we have attached 2 TGs per side of a copper plate. So here, in this case, we have to use 2 coolant modules, I mean heatsink with insulation box. So after analyzing, we realized that these are the results for our 5 models. When we are increasing the number of TEGs, we can see the temperature at hot side of TEGs is kind of reduced. It means that when we are having more TEGs, the amount of heat that copper plate could deliver is gonna be distributed between our TEGs. So each TEG would experience less amount of heat if we are going to use high number of TEGs. And also in the case of cold side of TEGs, you can see the temperature would increase if we are increasing the number of TEGs, and consequently we can see the delta T that each TEG would experience would be reduced if we increase the number of TEGs. And it's going to affect adversely the power output of our prototype. And the interesting point here is that if we are using 4 TEGs, but 2 TEGs per side of our copper plate, we can see the delta T is kind of compensated and is kind of higher than the prototype with 4 TEGs at one side of our copper plate, because in this case we are using another coolant module, so the cold temperature, cold side of the TEGs would have a better cold temperature. And here you can see our embedding process of our prototype inside of the asphalt mixture. And in figure C, you can see we have attached the thermal sensor in order to record the temperature variation over the time. And then we have tested our prototype in the laboratory. You can see we have developed 9 different prototypes, and here we have 2 size of TEGs, 4 centimeter and 6.2 centimeter. So we have 5 prototypes, includes the TEG with size of 4 centimeter, and 4 prototypes with the TEG with size of 6.2 centimeter. And in the left figure here, this is the prototype that includes the TEGs attached to the one side of our copper plate. But in the right figure, you can see the prototype that attached 2 TEG per side of a copper plate. And here we are employing 2 coolant modules. Well, and this is the results of our laboratory testing. the power output of 9 prototypes over 5 hours under 65, 55, and 45 Celsius degree. And in the right figure, you can see the temperature variation at 4 locations. And the blue graph shows the temperature of surface of our asphalt concrete. The red one shows the temperature at 3 centimeters below the surface of our asphalt concrete, where our copper plate is placed. And the yellow one shows the temperature at the bottom of copper plate where our TEG is attached, and the purple one shows the temperature inside of our heatsink. So here you can see the temperature over 5 hours remains constant over 5 hours thanks to actually PCM material inside of our heatsink. And in left figure, you can see the power output of our prototype, and the increasing power trend is kind of following the trend of temperature of our asphalt concrete. So if we have a higher temperature, so you can see our power output would be higher. And here we understood that if we have a temperature 65 within our asphalt concrete, the power range would be around 28 milliwatt. It means that the power difference between the prototype with large size TEG with high number of TEGs and the power output of the prototype with a small size TEG and low number of TEGs would be around 28 milliwatt. But when the temperature reduces, you can see the power range is kind of dropped. Eventually, when we have a temperature around 45 Celsius degree, the power range would be around 8 milliwatt. So we can here we can conclude that if we are going to select one of these prototypes for a region, for example, the region we expect the region would experience the high temperature around 60, 65 Celsius degree. So it is efficient to use the prototype with high number of TEGs and large size of TEG. But if we know that, for example, in another area that the temperature would be around 40, 45 Celsius degree, so in that case, it's not that much efficient to select the prototype with high number of TEGs or with a large size of TEGs. So because it's not gonna make a lot of difference in terms of power output. And also we have tested our prototype in the field. Here we try to provide the environment, the field environment as much as possible to mimic the realistic condition for testing our prototype. Here you can, we tested our prototype in July, and the power output we obtained was around 13 milliwatt. And also, again, we recorded the temperature at 4 locations: the temperature of an asphalt slab at the surface, the temperature inside of the heatsink, which is inserted in the soil, and the temperature of the plate, which is placed 3 centimeters below the surface of asphalt concrete, and the temperature at 10 centimeter, which was around 35 Celsius degree at 10 centimeter. And these are the conclusions that we have obtained. Actually, our design could produce power approximately 2 times greater than the other designs which are developed by other research groups in different universities. And our design coolant module could perform properly to maintain the temperature around 18 or 19 Celsius degree. And that's a good achievement for our project, because in other researches, we have seen that they were using soil or water to fill their heat sinks, but those materials could not maintain the temperature down because of the latent heat property of those materials. So the PCM could be a good option for cooling purposes. And also we realized that increasing the number of TGs will not increase the power output linearly. And as I explained earlier, because when we increase the number of TGs, the amount of heat that each TG would experience is kind of reduced. And also, if we are gonna use the TEG with size of 6.2 centimeter, it's better to make sure that in that region, the temperature of pavement would be enough to take the most advantage of this prototype. And also, our prototype could at least provide the power for illuminating 10 LEDs. So in remote areas where it's hard to see the intersections, we can illuminate the stop signs without demanding and relying on the power grids. So we can use this prototype in those locations to improve the safety and reduce the car crashes. And at last, this project was sponsored by the CPS Energy Department of San Antonio and carried out at University of Texas at San Antonio. And here I would like to thank my supervisor, Professor Desuki, for his continuous support. Thank you very much.
Thank you, Syed. Very interesting presentation. So since we don't have a buffer between the sessions, we're supposed to end at about 10:20. That still gives us another 5 minutes for any questions that we might have. I guess I can start off with a question. Do you see any opportunity for scaling this up even further?
Actually, yes. Actually, we are trying to maximize maximize the power output of this device. We are trying to find also more designs to identify optimized design to reduce the heat loss during the heat transferring, and for scaling up, we are trying to actually use the copper mesh instead of this solid plate. So in that case, we are gonna cover more asphalt pavement, and I think in that case, we will receive more heat and eventually more power output we can receive from that.
Great, thank you.
No problem.
We still have a couple minutes if there's any other questions.
And also, I would like to add another thing, that actually we had a joint project with the Department of Electrical Department of Texas A&M, and actually they have developed a structural health monitoring device, and we connected our prototype to that device. It allows to work that device. It's supplying the power for running that device. So it's kind of feasible to use this device for activating low power devices along our roadways.
It's not mine. It's the alarm. The alarm is going off.
Do we have a question there, or is that just? Okay, so any other questions, or else we can take a few minutes between sessions here? All right, well, thank you everybody for attending the Intelligent Transportation Systems session. Thank you for your attention. And we'll see you in a few minutes at the next session.
Well, thank you very much for your attention.